So some problems for chapter 3. So identifying some as a pure substance or a mixture, and classify it. So first one, A, that's a lead weight. So this is an element, it's a pure substance, and specifically it's an element. B, seawater, this is a mixture, it's a homogeneous mixture. And well, it should be uniform. I guess if it's very turbid, you could argue it's a heterogeneous mixture, but this would be a homogeneous mixture. I'm assuming a nice, clean, clear seawater. Sea distilled water. This would be a pure substance, and it would be a compound. And then finally, Italian salad dressing. This is definitely heterogeneous. You have to shake it up, and if you haven't seen Italian salad dressing, I mean, most Americans know what it is, but if you're not familiar with it, there's little bits of like peppers in there, so you can clearly see it's non-uniform, and it has phases too, and you have to shake it up to bring the phases together. So this is definitely a heterogeneous or non-uniform mixture, and so there we go. Let's identify these as physical or chemical. Physical properties involve not changing the compound. It's just observing something without changing. Chemical is something you observe by changing it. So tendency of copper to turn green when exposed to air. This is a chemical property because then the tarnish is a chemical reaction. The tendency of automobile paint to dull over time. This is a little ambiguous. If it's a I'd say it's a chemical I'd say this is a chemical reaction because it can do that. It depends, though. I guess it really depends what's causing the paint to dull. If it's from a physical process, then it's just like if it's just from rubbing, then that would be a physical process. But if there's some sort of chemical reaction going on, then that could be a chemical change. So this is a little ambiguous. We'll see what the it does decompose. Okay, so it decomposes due to the reaction of oxygen or sunlight. So it's a chemical property. I was just wondering with the paint being dull, and it could be from like rubbing, for instance, and then you could argue it's a physical change. Tendency of gasoline to evaporate quickly, that's a physical property. You're not changing gasoline; it's going to a gasoline vapor. The low mass for the density. So the density of aluminum, that's a physical property. That's not that you're observing the density of aluminum without changing it. So conservation of mass. Let's do this. A chemist forms 16.6 grams of potassium iodide by combining 3.9 grams of potassium with 12.7 grams of iodine. Show that these are results verify the law of conservation of mass. Well, the reactants equals the mass of the reactants, total mass of the reactants equals the mass of the products. Therefore, the conservation of mass holds. Let's convert some units here. A candy bar has 225 capital C calories of energy. How many joules is this? A capital C cal is 1,000 joules. I'm sorry, that's 1,000 calories, which in a calorie, let's do the conversion. So convert calories to calorie and then convert to joules, the 4.18 joules per calorie. And here are some conversions here. And let's go ahead and solve that. So 225 kilocalories, then times 4.18 for joules, and then we're given then to the answer in 3 sig figs, 9.41 times 10 to the 5th joules. So again, just doing dimensional analysis and getting the units to cancel. Let's talk about exothermic and endothermic reactions. So wood burning in a fire, like if you were to touch it, it's hot. So if it's hot, it means heat is leaving. It's exothermic. Ice melting, if you put ice in your drink and it melts, it cools the drink down. That means absorbs energy. That's endothermic. So let's convert between temperature scales. Negative 25 degrees Celsius to Kelvin. We have to know the equation. So Kelvin is degrees Celsius plus 273.15. And then apply the equation. And of course, we don't know the decimal place because of the rules of sig figs, and then negative 25 Celsius is 248 Kelvin. So let's convert between Fahrenheit and Celsius. Again, you have to know the formula, and this is the formula. Degree Celsius is Fahrenheit minus 32 divided by 0.18. So let's go ahead and apply this. So 55 Fahrenheit minus 32 divided by 0.18 is then to 2 sig figs is 13 Celsius. So let's look at radiating heat energy to temperature changes. And so if you look at this, so gallium melts at 29.9 degrees Celsius. If you hold it in your hand, it melts from your body heat. How much heat must 2.5 grams of gallium absorb from your hand to raise the temperature from gallium from 25 Celsius to 29.9 Celsius? The specific heat capacity is 0.372 joules per gram degree Celsius. And if you look at this, then you have to use the equation, the Q equals mc delta T, the specific C being the specific heat capacity. And now we got to find the terms. So first of all, the delta T is temperature final minus initial. So get a delta T, and we have the mass, we have the heat capacity, and then put in the equation, the mc delta T, and 2.5 grams times the heat capacity times the change in temperature, and we get 4.6 joules. Also note, this is just the energy it takes to bring it up to melting point, not necessarily to melt it. The act of melting takes more energy, but this is the energy it takes to raise the gallium up to its melting point. And we're done.